I am very excited to be here and talk to you about all the things that can go wrong with OAuth. Who here is familiar with OAuth, or at least what it is? Almost everybody. Great. Okay. That's wonderful. So, a little bit about me. Introduce myself. I'm Aaron Parecki. I maintain OAuth.net. This is the community website of OAuth. If you ever Googled stuff and tried to research OAuth, you've probably landed there. I also am a contributor to the spec, so I've been working on this document lately, which is talking about best practices for OAuth in JavaScript apps. And I also wrote a book, finished it a couple years ago, and we have some copies here we'll give away at the end. It looks like there's a very full room, so I don't think everybody's gonna be able to get one. So we'll have to figure out a way to do a contest for that or something. I also work at Okta. I'm on the developer advocate team, and we have a lot of, obviously, we provide OAuth as a service, and so I write blog posts on our blog as well sometimes about OAuth and these concepts. I do want to throw out this disclaimer. They didn't ask me to put this in, but I just want to make it clear that this is not necessarily representing the views of Okta, and also I am calling out specific companies in this presentation, not to pick on them and not because I don't like them, but because they are good examples of when things don't go quite right. So it's not to blame them necessarily, but yeah, you will see some companies named in here. So before we get started with what all can go wrong with OAuth, I want to start and back up a bit and provide some context about why we even have this in the first place. What problem is this solving, and what was it created to do, what was it not created to do, things like that. So back in the dark days of the internet, this pattern popped up all the time. You would have a new app like Yelp. When it would first launch, obviously there's barely any users and no friend network yet, so they would say, hey, let's see if any of your friends are using Yelp. And they would ask you to put in your email address and the password to your email. Now, at this point, you're probably all thinking, that seems crazy. Why would I ever do that? And you're right that that is just not a thing we do anymore. We understand this is terrible, but this was a very, very common pattern. Even like Facebook was doing this. And if Facebook tried this now, like, no way, right? But people were very willing to do this because they wanted the end result of what that was, which meant that this app could get their contact list and then see if any of the friends were already on the network, and they would already have friends in the new app. So what we're trying to do here is let Yelp access your contacts from like the Google Contacts API, but we obviously don't want it to access your actual email. And Yelp also doesn't want access to your email. They were just trying to get your contact list. But before OAuth, there was no way to do it other than ask for your password. So we can try going through a couple of other ways of doing this, right? Like obviously Yelp can't just say to Google, hey, give me this person's contacts. That's not going to work. We can't have the user give the password to Yelp to then take it to Google, because that also doesn't work for the same problem, for the same reason. So the actual problem here is, how can we let Yelp access data in Google, but without giving it your password? And that is what OAuth was created to solve. And now we have this pattern where now when a new app like Yelp launches, you see this button, connect with Google, connect with Facebook, connect with whatever has the data that's trying to be accessed. And this acts as a buffer between giving your password to Yelp and then giving it just the data that it wants. So now we have this situation where the app actually needs to ask the user for permission to access the data, and then instead of the user typing in their password into Yelp, they type their password into Google Contacts. That then returns back an access token, and then the user can take that to Yelp. Yelp can then access the Google Contacts API with the access token. So that actually ends up looking like this is what it looks like when it's used. Is it's set in the HTTP header. It's passed along with the HTTP request. But I like to think of it like a hotel key card, where you go to the hotel and you check in and you give the person at the front desk your ID and you prove to them who you are and give them a credit card payment. And then they give you back this hotel key card. And the key card is like an OAuth access token. You take that key card and you go to the door and you swipe the key card on the door. Now the door doesn't care who you are. It could care less. All it cares is, does this card have access to this door at this time? So that is why it's analogous to OAuth, because there isn't necessarily user identity encoded in the access token. There doesn't even need to be a unique user ID or any profile information. All that's encoded in there is the access information. Can it access this thing? And then, of course, when you check out, your key card expires, right? Just like an access token expires. So let's talk a little bit about how this works in OAuth and all the different players involved in this. In OAuth, there are basically these 4 different roles. And the 4 roles are need to pass data back and forth between each other. So we start with the device the user is using. That's going to be either their laptop or a mobile phone or Apple TV or whatever the device is. And then there's an application that the user is accessing. The application might be running on the device. Like if it's an iPhone, there's an iPhone app on the iPhone. The application might be on a web server remotely, and then there's a connection between the device and the application. And then the OAuth server is a thing that's going to be generating tokens and validating tokens and asking the user for permission, things like that. And then separately from that is the API, which has the actual data that's trying to be accessed. So in like really small systems, like if you imagine a Rails app, the OAuth server and the API are probably actually the same code base running on the same server in the same data center. They don't need a communications channel between them because they just share code. But as soon as you start getting into larger scale deployments, using services for different aspects of things, or if you don't have just one API, but you have a bunch of smaller microservice APIs, then those are going to be separate, physically separate from the OAuth server, and they need a way to talk now, right? Okay, so there's all these different players, and they may exist in slightly different configurations, but conceptually there's still 4 separate things. And the data needs to move between all of these somehow. So let's walk through the most common OAuth flow, which is the authorization code flow. So this starts out by the user visiting the application, either launching the app on their phone or visiting the website in a browser and clicking the login button. The act of them clicking the login button is basically them saying, hey, I would like to use this application. And the app says, great, please go to the authorization server to grant me access. And that's going to be like a redirect in the browser. That causes the user's browser to land on the OAuth server, where it says, hey, I would like to log into this app, and it wants to access my photos. That's going to be encoded in the query string. At that point, the OAuth server says, cool, here is the request the app is requesting, shows that to the user. If the user clicks allow, the OAuth server will generate a temporary code, a one-time use code, and give it back to the browser. And that's going to be, again, via a redirect. That causes the browser to go back to the app and say, hey, here's this temporary code. Please use this to get a token. And now, behind the scenes, the app can go and talk to the OAuth server and say, hey, here's the temporary code the user gave me, and here's my client secret. Please give me a token. And the server can respond with the access token, which it can then use to make requests. Follow all that. It's kind of a lot, but hopefully that wasn't too much. If you notice, there are 2 colors on the screen here, and the bottom 3 are pink. I colored those differently because there's something special about those requests. Those requests are sent over a back channel versus the whole first part of the flow, which is all front channel requests. Let's talk about this for a sec. Back channel requests are, you're already familiar with them. It's just the sort of normal HTTP client. You're a client, you talk to a server, and you get a response. That is great because the connection is over SSL, can't be tampered with, et cetera, et cetera. That's a sort of normal baseline thing. The front channel request is the less straightforward one. And that's the idea, which is that because these 2 parties don't have a way to communicate directly via a back channel, we actually have to use the user's address bar to send data between them. So the user is stuck in the middle, and the address bar is going to be the thing that carries the data from the authorization server to the client. that means there are a lot of things that can fail in this process. There's DNS issues, or the user can just manipulate the URL. Other software on the machine can manipulate the URL. So let's talk about why we use these two different things. Benefits of the backchannel. When the application is talking to the OAuth server, it's going over SSL, can verify the cert, it knows it's talking to the right server. That connection, because it's over SSL, can't be tampered with. We know that it's a secure line. And importantly, the response that comes back can be trusted immediately because it came back in the same SSL connection. It was not a new connection. So it's kind of like delivering by hand the access token to the thing directly and handing it off. Whereas sending an access token back in the front channel is like lobbing it in the air and hoping that the app catches it. So why do we use the front channel at all then? So it does have some benefits. It enables the user to be involved in the process, which is an important part of OAuth, which is getting the user's permission. And it also means that the thing on the receiving end doesn't need a publicly accessible IP address, which is the case for things like mobile phones or other or browser-based apps, or things that are not just a web server running in the cloud somewhere. This, of course, comes with a bunch of risks, though. The sender, from the sender's point of view, it has no guarantee that the receiver is actually going to get that information. Also, because it's actually using the address bar of the browser, that's going to be written to the browser's history. So that might be stored on disk. It might be synced to your Google Web History thing, which may then end up on another device. So it's really just out there. From the receiver's point of view, if you ever receive data over the front channel, you have no reason to trust it until you can verify it somehow, whatever that verification looks like. Okay, so let's start talking about things that can go wrong in the process here. There's basically a lot. The answer is a lot of things can go wrong. There's everything from like stolen API keys, which is a pretty straightforward one, stealing access tokens, intercepting that redirect URL to be able to mess with stuff. Even phishing is still a problem with OAuth. OAuth doesn't actually solve phishing. It just has a different kind of phishing problem. There's so many things that can go wrong that there are entire documents dedicated to describing them. So RFC 6749 is the core spec, which is, has its section 10 is the security consideration section, which is a nice long list of things right off the bat that were known things that can happen when you are building this system that you need to protect against. Then there's RFC 6819, which is the original threat model and security considerations document, which is a separate document describing these problems and new problems. And then there's a recent document, which is not even our RFC yet, but it's in the works. It's up to 11 drafts. And that is called, it's a best current practice for OAuth. And that one, again, describes a lot of these things of, depending on the different deployment scenarios, of what can go wrong and how to fix it and how to best handle this. Okay, so let's look at some examples. Let's start with Twitter. Twitter is a fun one because this is an old one, and this has been long solved. But 2013, these headlines came out, which is the Twitter OAuth API keys were leaked. So what's going on here? The Twitter apps, like mobile apps and all the various platforms, they needed API keys in them in order to do the OAuth dance to Twitter's own API and sign API calls. So Twitter put their own API keys into their apps, shipped them to the users, and then, of course, it's a binary file that ends up on a user's device, so it's super easy to just pull out strings out of the app. So someone did that. Someone went and cataloged all the Twitter apps and then posted all the credentials on GitHub, and then all these headlines came out of like, oh my god, all the Twitter API keys were leaked. How were they stolen? Well, geez, how were they stolen? They were just in the binary file. It's not a secret, right? And the end result of this is that anybody can now impersonate the Twitter apps. So if you think about it, that doesn't necessarily do a ton of damage by itself, but it does do things like, this was back when Twitter was starting to really crank down on rate limits for third-party apps. So if you were able to get an access token using Twitter's own credentials, you can get around the rate limits. A more subtle one, which would be a little bit harder to pull off, but you totally could, is to actually impersonate the Twitter app for your victim and have them end up authorizing your app and they were thinking they were logging into the real Twitter app. The moral of the story is don't put secrets in native apps. They are not secret. It's just not possible, which we understand now, and we've come up with solutions around that. This is a blog post I published a couple weeks ago describing a couple of the nitty-gritty details about how exactly you can get secrets out of mobile apps in case you need to cite that to somebody. So how does this relate to OAuth? Well, we can't use a secret in a mobile app in OAuth, which means we need a new solution. And that is what PKCE was created for. So PKCE, Proof Key for Code Exchange, is, again, it's a new RFC because the way that OAuth spec development works now is everybody's, all these things are developed as extensions to the core and not replacing core. And yes, it's pronounced PKCE, because I guess it's cute. What PKCE does is it takes the core authorization code flow that we saw before, and then it's going to add a step to the beginning and to the end. And that is going to essentially replace the need for the client secret. So we're going to take a look at this flow diagram again and see how PKCE changes it. So it starts out the same. The user says, I would like to use this application, clicks the login button on the app. Now, before the app starts, it says, cool, hang on, I'm going to go make up a new secret, and I'm going to hash it. So hashing is the idea with using the hash value is it's a one-way operation, so that if an attacker can steal the hash, they don't know the actual secret that was used to make the hash, right? So it creates the hash, and then it tells the user, all right, please go to the authorization server to grant me access, and take this hashed value with you. The blue line means it's a front channel request, it's in the address bar, but it's only the hash value in the address bar. The user then ends up on the authorization server with a bunch of stuff in the query string, which says, I would like to log into this app, and here's the hashed secret it gave me. So setting things up, right? Then it's the same as before. The OAuth server says, cool, here's a temporary code you can use. The user takes that temporary code back to the app and says, please use this to get a token. And now here's where it's different. Instead of the client secret here, the app actually sends the plain text secret that it generated in the first step. This is a back channel request. This is not being sent in a browser, so it's fine to send a secret here. It's also a one-time use thing. It wasn't deployed for this. It wasn't globally deployed to this app. It was set up for this one request. That step means that the authorization server can then hash that secret and compare it to the hash of the original, and now it knows that this thing exchanging the code is the same thing that started the flow. So this is great. This is how it all works under the hood. Thankfully, you don't actually have to worry about this if you are actually just writing an app, because it is usually all handled by libraries. If you are using a service's own SDKs, like the Okta SDK will do this for you. If you're using a service that doesn't have its own SDK, then the AppAuth library is a great library to use because it will handle all this under the hood, and you just kind of get a nice friendly API to work with. But that is how to solve the client secret problem if you just don't use provisioned secrets in mobile apps. All right, let's talk about stolen access tokens, or probably more accurately called improperly issued access tokens. This was a problem that Facebook dealt with very recently. This was the headline, 50 million Facebook accounts were hacked. Who remembers these headlines? Yeah, okay. It's only a few months ago. So a lot of people were saying this was like stolen access tokens or whatever it was, but because it's Facebook and because they're so big and everybody is just watching them like a hawk now, they actually ended up putting out a lot of information themselves about exactly what happened here. So we can actually go to the source and see what they said about the attack, which is otherwise we would have no real idea what happened. So if you click on that Facebook newsroom link, their own security update, the first chunk is like for the press of like the vague description of the problem. down below is the technical details. And that's where we get to the fun stuff. So in that, they say, the vulnerability was the result of the interaction of 3 distinct bugs. Now, they're not all related to OAuth, and also this is only kind of vaguely related to OAuth at all, but I still think it's relevant. So the first bug has nothing to do with OAuth. The first was they have this feature called View As, where you can go to your profile page, click View As, and type in somebody else and see what your profile looks like to them. That's a very cool feature. I am like props to them for building that. That's great. It helps with the whole transparency thing. It helps people understand the privacy controls that Facebook has. That's great of them to do that. Okay. There was a problem with the View As feature. It incorrectly provided the opportunity to post a video. So that's not like that bad by itself, because really all that means is that if you click on your profile and click View As, you're going to see a prompt to upload a video to your own page. Whatever, right? Not a big deal. Hold that for a second. That's the first bug. Second bug. The video uploader had a bug where it would generate an access token that instead of having the permissions to upload a video, actually had permissions of the Facebook mobile app. So this is starting to get into a little more OAuth territory here, right? The problem here is that there should just never be a way for one app to act as another app. That should never have been a thing that could exist. So something is clearly wrong with their internal implementation here. So that's the second bug. The third bug, when the video uploader appeared as part of the View As, it generated the access token not for you, the viewer, but for the user that you were looking up. This one's where it gets weird. What? Like, how did this even happen? How could it be possible that an access token for the user you're looking up ended up in your own browser? That is a very bad bug. So but again, by itself, it's maybe not the end of the world, but when you stack all these 3 things together, you go to your profile, you use the View As feature, that would cause the video uploader to appear, which would generate an access token for the other person. Because of the bug in the video uploader, it would have the permissions of the Facebook mobile app, which basically means it can do literally everything as them. That's how did this happen, right? So how do you fix this? I mean, I don't know. This is like a couple of pretty bad bugs stacked up together in a bizarre way that it would be hard to see this coming. I give them that. I think one of the things that you can do to overcome this and avoid putting yourself in this situation is not giving complete trust to the different components of your app, even when you think it's fine, because it's all part of your system. So the same way that you don't trust third-party developers with the same permissions that you trust your own developers, like just start thinking of the entire part of your system that way, where you treat everybody as an adversary and you do things to protect yourself against your own internal teams the same way you do against third-party developers. And there might still be bugs, but this should help cut down on the number of ways they can be stacked and overlapped and to cause these bizarre situations. Okay, the next one is a subtle one. So JWT, pronounced JOT, stands for JSON Web Token. This is very commonly used as, JSON Web Token is commonly used as a way to encode OAuth access tokens. So you'll end up with putting a bunch of stuff about the access token into the JOT and then giving that to the app as an access token. So what happened here is, this was 2015, and there was basically a bug in a whole bunch of JOT libraries that could cause anybody to just modify the data in the token and whatever, impersonate somebody else or change the permissions of your own access token, things like that. So let's look at what this looks like under the hood. Here is an example JSON Web Token. It at first glance, looks like a long random string. It is not. There are 2 periods in there, and if you split on that, there are 3 parts. The first 2 parts are base64 encoded JSON data, which means this is basically plain text. If you look at this data, you just copy and paste it into a base64 decoder online, you will see what's inside of it, and it'll look like this. The top part is the header. The header describes things about the token. The middle part are what's called the claims, and that's basically the data that you actually care about. It's things like the user ID, the expiration date, the permissions, whatever else your access tokens include in them, get included in the claims. The bottom part is the signature. And the idea here is that if you create a JOT, you use a signing algorithm like using a public-private key. You sign the top 2 pieces with your private key. That creates a signature, which you can then put as the third part. Because it's a private key, the only way to sign these is if you have the private key, and anybody out on the internet can't just go and change the data without causing the signature to fail. So what was wrong with all these libraries? Well, the top part, the header, describes stuff about the token, including describing the signing algorithm used. There is, turns out, also a signing algorithm in the spec called none, which means there is no signature. So if you had a JOT and you could change the algorithm text to none and then re-encode it, leave off the signature, pass that to a library, and it would be like, OK, cool, let's see, algorithm none. Great, done, you're in. What? That one's pretty bad. The little more subtle version of that is that you could actually change it to a shared key signing algorithm where there's still a signature, but if you found the public key of the thing that signed this, you could actually use the public key as a shared secret, compute the signature again, and you would get the correct signature. So the decoding library would think that it's checking the signature, which it is. It's just that it's checking it with a shared secret, which you could make it do. So that's also bad. The moral of this story is basically that you just can never let the JOT header determine the verification mechanism. If you think about it for a sec, this makes complete sense because like when you're writing a web app, you don't trust random stuff on the internet when it comes in until you verify it somehow. And you're trying to verify this JOT, which means you can't use external data to verify it, otherwise you're not really verifying it, which is what all these libraries were doing. They were using the untrusted, not yet verified header to determine whether the token was valid. So thankfully, most of these libraries, I'm pretty sure all of them, got patched and updated very quickly in 2015, 2016, when all these headlines came out. So now, if you are using a library to do this, basically that signing algorithm is just ignored because you have to, in your code, say which algorithm you want to use to verify the JOT. So that's basically the solution, is don't use untrusted data from the internet. Fancy that. OK, last one. This one is this one's really tricky. This is an OAuth phishing attack. And this one's really hard because it is not obvious what the solution is, like any phishing attack, right? This was 2017, and it's called a few different things. Phishing email, OAuth worm, Google Docs worm. But basically what happened is this email was sent out, and it included a link where if you clicked it, you would see an OAuth prompt on Google. So who can tell me what's wrong with this picture? Anybody see anything wrong with it? This is actually on accounts.google.com. You're in your real browser, got your verified SSL certificate, you're on the real domain, but then you see this prompt. So this by itself doesn't look particularly suspicious, but what if you click the little drop down there and see this? So now what's wrong? docscloud.info sure doesn't look like Google to me, right? So what's happening here is the attacker went to the Google Developer Console, created a new application named it Google Docs, uploaded the Google Docs icon, got a real client ID and a real client secret, and then created this URL, which is the way that you kick off the OAuth flows. And all it takes is one person to click that. Because as soon as one person clicks this, the attacker now has an access token, which can send email from their account and read all their contacts. So then the attacker goes, downloads the contact book, then uses the Gmail API to send an email to all of their friends that says, hey, I've invited you to view this document. Click here to open it. And this is what Google does, right? Google sends this email when someone shares a file with you. And this bottom one's the fake one. The tricky part is that this is not really a spam email because this is coming from a real Gmail account because it was used with a real access token that belongs to that user. And it's being sent to one of their friends. So it's not going to get flagged as spam because it's someone in their address book and it's coming from the real account. As soon as they click that, they see this prompt, and now they're already primed for, okay, I'm going to view this file in Google Docs, so I'll just click OK. And this happened so fast. In the span of about 40 minutes, it was like up to millions of accounts had been compromised, and Google actually had to tweet this out, and they were investigating this problem and hadn't yet solved it. And about 20 minutes after that, they were like, oh, this is what's going on, and they just disabled the client ID. And the next time that anybody clicked that link, they would see this error page. So they blocked that from spreading further, but do they actually solve the problem? What is actually the problem here, right? Well, it has to do with this consent screen, the asking the user for permission. The trick with that screen is that you need to do a couple of things in that screen as the OAuth provider. You need to make sure you're providing the user information about what the request is. This app is trying to access these parts of your account. It wants to read your email, manage your contacts, upload your photos, whatever it is, right? It needs to provide that in enough detail that the user actually understands what's going on, but not so much that they're just scared away and click OK. So here's Google's. And they actually do a pretty good job, but the one thing that's missing is that they don't actually tell you that this is the real Slack app. It just says Slack, right? How do you know it's the real Slack app? But at least they do a good job with the scopes. So if you click on one of the little information icons, you get more details about what these permissions are, which is good because Google has hundreds of APIs. But let's look at some other examples of other companies' consent screens. This is Wunderlist. I think this is I like here that they have the red and green separating what the app can do and what it can't do. Makes it very clear to the user that the app will not be able to delete their account, for example. I think this is not particularly well branded. If I suddenly was found this, encountered this screen on the internet, for example, if somebody sent me one of these little phishing links, I wouldn't necessarily know that I'm on Wunderlist. Okay. Here's Flickr. Flickr is one of the older OAuth implementations. They were part of developing the spec. Been around for a long time. They again do the thing with the green check marks and the red X of here's what the app can do, here's what it can't do. They actually used to color both of those buttons blue so that you were forced to read it because there was no primary target to click. But I guess they walked that back. Here is Spotify. Spotify, when you are authorizing an app to access your Spotify account, you'll see this prompt. And this is not very well designed, in my opinion. The things that the app will be able to do are track what you listen to and receive the account data. And those are in 2 different font sizes and 2 different font weights. Why couldn't that be consistent? Also, I don't know why there's such a large blob of text there that no one's going to read. Here's GitHub. GitHub does a pretty good job. And they actually do one thing that would very likely lead to fewer phishing attempts, which is at the bottom, one, OAuth 2 example app by Aaron PK. They put the name of the GitHub account of the developer of the app. So that's one. If this was somehow saying hey, Gist wants to access your account, it would say the Gist app by not GitHub. And you'd be like, that seems fishy. The other thing they do is at the bottom, they tell you where you'll be sent back to after you successfully authorize the app. So again, it's another clue to the user that that may not be the real app that you think it is, if that URL looks suspicious. Here's Facebook. Facebook has an interesting feature which the OAuth spec allows and almost nobody takes advantage of, which is edit the info you provide. The app is going to request some information from the user, but as the user, you can actually go and say, all right, click that. Maybe I don't want it to access my friends list, even though it requested it. And then it's going to generate an access token that doesn't have that permission, which is pretty cool. Fitbit does that as well. So an app can request access to all of your Fitbit data, and then you can actually go and uncheck, be like, actually, this app doesn't get access to my location information. So if we boil all these down and look at what they all have in common, we can come up with a sort of prototype OAuth interface that is going to cover most of the bases here. So identify the service that the user is logging into so that they know which account we're talking about. Identify the third-party app, both the name of the app as well as the URL of the app and the developer name, all these clues to help the user understand whether or not this is a legitimate request. The account that's logged in, users often have multiple accounts at services. So you need to make sure that they know which of their own accounts they're about to be granting access to. And list the scopes the app is requesting. So that is, again, like often a challenge because you may have a bunch of different scopes in your API, and you need to find a way to concisely describe that to the user. And then, of course, the allow and the cancel buttons. So yeah, this was a tough one because OAuth wasn't really hacked. It was just a phishing attempt, and the only way to really solve that is by educating users and helping users understand what's going on, which is a very hard problem because it's a people problem. So that is, hopefully that gives you some context for this. More information on all of these things and links to all these documents are on oauth.net/security. And I will be hanging around here this afternoon. We have an Okta booth out in the expo hall. I'll be there for the rest of the day. Find me there. I have cat stickers. And we also brought copies of the book. So if you're interested in this, the book goes into a lot more detail. It talks about both building apps from the application's point of view, also building OAuth servers. We have them at the back. Feel free to stop by and grab one on your way out. So thank you. We have for questions here. Otherwise, I'm happy to talk more about this at the booth and later this evening. Yeah.
It struck me as weird that Facebook had like access or secrets for different components of their app. Is that common? Or
So the question was, is it common that like Facebook would have different secrets for different components of the app? Yeah, that is a pretty common architecture when you're getting to the scale of companies like that. Well, even smaller than Facebook. Facebook's enormous, but it is very common to treat different components of your app as different OAuth apps internally so that you can better isolate these things.
And like Facebook would internally trust themselves pretty well. So like the idea of OAuth being like delegation,
yeah.
Sort of feels overkill.
OAuth sort of feels overkill in that situation because it's not really a third party, but at the scale that they're operating, they almost are. And if you look at Google as another example, Google has a team that does accounts.google.com. And if you're like someone on the Gmail team or someone on the Google Contacts team, you don't touch the accounts team at all, right? And you're basically treated as a third-party developer. And for good reason, because the accounts team has no reason to trust the random Google developers over there in the corner doing whatever new product Google is launching tomorrow, right? So I think that does lend it, the OAuth framework and the idea of at least issuing access tokens that have more limited scopes is a very useful construct, even internally.
Scopes, because that's actually something we're
yeah.
grappling with right now. And do they use like similar scopes to their public clients, or do they sort of have like a broad scope internally?
So the question was, do they use similar scopes internally to their own clients? I'm not totally sure about that because a lot of that stuff is not actually visible to you as the end user. It would take a lot of digging. Not totally sure on that. I would imagine they do, though. If you don't make it out of here before the books are gone, let me know. I have a couple extra stashed. Yeah.
So you mentioned the front channel and back channel
Yeah.
for exchanging tokens and stuff like that. Is there any way? So I'm a currently mobile developer, and so my question is, the front channel exchange of tokens is kind of awkward on mobile. You have to like go out to a web view, and then it redirects inside of the web view and pops you back into your app. Is there any better way to do that on mobile? I assumed that it was done incorrectly.
Yeah, so the question is on mobile, the sort of idea of using the front channel is kind of awkward because it involves a browser. For first-party apps on mobile, it's not uncommon to use straight-up passwords still and exchange a password for an access token, which is better than not using any of the OAuth framework, but you would never want a third-party developer to do that. It isn't as bad now because the platforms have been developing things to make that process smoother. So if you've noticed on iOS, when you click like a login with Google thing or any of the Google apps, the browser now pops up within the app, and you can still see the address bar, and it's a system browser, so you share your cookies, so you're already logged in, but the app can't view inside. And that is the best we have right now for mobile for actual, third-party delegated OAuth. And it is definitely better than it was like 5 years ago. But I agree, it's not something you necessarily want to do as a first-party app, which is why for first-party apps, some people do just use straight-up passwords still. Yeah.
You mentioned that the access token doesn't necessarily have user information in it, right?
Mm-hmm.
Expect that I need to figure out who the access the data that
So.
Once you're finished speaking to the speaker, we're asking you to clear the room so that you can see the badges of everyone who comes in later. Thank you.
Okay, thanks. Sorry, your question was?
the access token itself.
Oh yeah, the access token doesn't necessarily have user data in it, information in it. So how do you know who the user is? So there's two answers. One is the way it was done before we had OpenID Connect, which is that most of the servers would put up an API endpoint that would just return user data given an access token. OpenID Connect has now standardized a way to exchange user data, and it's built on top of OAuth, so the flows all look the same, but instead of an access token coming back, you get what's called an ID token, which does explicitly include user data. And you have to ask for it separately in addition to or instead of an access token, depending on what you're doing.
If there's a REST API that makes an access token, that should also ask for an ID token?
You have to ultimately read the docs for whatever service you're talking to as to whether it supports it. But if it supports OpenID Connect, that's the way to get the user data for whoever just logged in.
I see.
Yeah. But like GitHub doesn't support OpenID Connect, so they only do OAuth, but they have a special endpoint where if you can send an access token to them and it'll tell you who it belongs to.
Right. Okay.
Yeah. Cool. Thanks for all the questions. Make sure, so you grabbed a book. I will give you one, and hopefully the other guy got one. Thanks for coming, everybody.